Lab 3, Black Hole. The objective of this lab was to determine the mass of a black hole from motion data of the star in orbit given in a CSV file using a computational model using physics concepts we have learned, such as the fundamental principle, Newton's second law / the momentum principle, and Newton's law of universal gravitation. I analyzed the relationship between net force and changes in the momentum. The mass of the black hole was found to be 3.58 times 10 to the 31 kilograms. The physics. There are two main concepts that are applicable to this lab: the momentum principle and Newton's law of universal gravitation. Newton's law of universal gravitation states that there is a force of attraction between all masses in the universe. This force of gravitational attraction is directly dependent upon the masses of both objects and inversely proportional to the square of the distance that separates their centers. Newton's conclusion about the magnitude of gravitation is summarized symbolically as seen here. We manipulated and used this expression to find the mass of the black hole. We see in the momentum principle that the change in momentum of an object over the small duration of time is equal to the net force of acting on that object. We also use our knowledge of how momentum changes when an object's motion speeds up or slows down or curves due to the parallel and perpendicular components of the net force acting on the object. That relationship is expressed here. Creating the model. We were given several important initial conditions to create the model through code that would help us find the mass of the black hole. Here we have the star's mass, the position of the black hole, and the delta t, which was given. Here's where the star's motion data was inputted using the CSV file provided. The first while loop calculates the velocity of the star during its path around the black hole. In the second while loop, we define the star's v final and v initial. After that, we are able to calculate the initial and final momentum by multiplying mass times velocity. From there, we can find delta v and delta p. We can now compute dp dt, the change in momentum over the change in time, which according to the momentum principle equals F net. Then we can find the direction of momentum, p hat, by dividing the star's momentum by the magnitude of momentum. Using this information, we can find the parallel change of momentum over time, dp dt parallel, by multiplying p hat by the change in magnitude of momentum over the change in time. dp dt parallel is equal to F net parallel. Because dp dt equals dp dt parallel plus dp dt perpendicular, we can calculate dp dt perpendicular using that relationship. The value of F net perpendicular is equal to the value of dp dt perpendicular according to the momentum principle. Now, let's run the model. When we run the model, we will see that the green line represents the path of the star. The yellow arrow represents the net force acting on the star, which in this case is gravitational attraction. The blue arrow represents F net perpendicular, which at any point points towards the center of the Kissen circle, and the black arrow represents F net parallel, which points in the direction of the motion of the star. Now let's go back to the code. Here is where we calculate the mass of the black hole using the magnitude of the gravitational force, which is the same as F net in this case. We print this variable, the black hole's mass, in the shell window, which we see right over here, 3.58 times 10 to the 31 kilograms. What does it mean / what if? F net and F net parallel and F net perpendicular all have the same value in units as their counterparts dp dt, dp dt parallel, and dp dt perpendicular. We know this relationship between the F nets and the dp dt's because of the momentum principle / Newton's second law. But they are not the same because they are fundamentally different things. F net parallel, and F net perpendicular all affect an object's motion as they are the sum of the forces acting on an object. dp parallel, and dp perpendicular describes the object's actual motion and how that motion is changing with respect to time, as in whether or not it is speeding up, slowing down, turning around, curving, etc. What if? I would not be able to tell the difference between the black holes if the motion of the star is exactly the same. Because the motion remains the same, using the motion data that's still given, we would find that the mass of the new black hole to be the same as the original black hole.